Go.
Okay. I'm going to begin by sharing the screens. Put this on play. Okay, can you all see what I hope you're seeing?
Yes.
Modern cosmic distance ladder.
Right. Not a problem. Quite good. Thank you.
Okay. So this is pretty much where we left off last time. If I can refresh your memory, the task was to describe some of the direct or local ways of determining the Hubble constant, which involved determining the velocity of recession and the distance to objects. And one had to go out fairly far into the universe before you were looking pretty much at the Hubble flow and not random velocities. And the modern determination of the Hubble constant by that method relies pretty much on three steps. The first one being the parallax, which was greatly aided by the Gaia satellite, enabled it to get to well into the region where Cepheid variables were located, and that these Cepheid variables could be calibrated, and they then were used to calibrate the third distance indicator, which were the type 1a supernovae. And we came out with a Hubble constant of about 73 kilometers per second per megaparsec. And let me remind you that a parsec is about a little over 3 light years, if you think light years instead of parsecs. Okay, so that brings us up to a completely independent way of determining the Hubble constant, which is basically cosmological in nature. So a very, very, very brief, broad brush review of cosmology and cosmological models is the following. The scale of the universe and its current expansion rate are governed by two parameters. I've called them A of t on top, which today has the value of unity. In prior epochs, it's smaller, reflecting the fact that the universe in past was smaller than it is today, in the sense that the distance between two clusters of galaxies, say, distance between clusters of galaxies, has been expanding as the universe ages. And so if you go back, it goes the other way. The Hubble constant is the current rate of expansion of the universe. And the equation governing A of t are the so-called Einstein-Lemaitre-Friedmann equations. Mention them, we're not gonna look at them really. But they depend on the contents of the universe, what's in the universe and how much is in there, and of course on the initial conditions. The geometry of the universe, whether it's positively curved, flat, or negatively curved, depends on, again, on the sum of its contents. There's a critical density of the sum of the contents, the critical energy density for which the universe would be flat, the geometry Euclidean. Less than that critical density, the universe is negatively curved. Greater than the critical density, it's positively curved and folds back on itself. And the contents that we know about today, and that we incorporated in our models are photons, neutrinos. These are relativistic particles in the sense that they travel at, well, photons travel at the speed of light, neutrinos almost at the speed of light, baryons, which are electrons, protons, ordinary stuff. And then these two components, cold dark matter and cold dark energy. Cold dark matter is, we don't know what it is. A good guess is that it's particles that we don't interact electromagnetically with particles that we're made out of, so we don't see them. It's transparent. They're cold in the sense that they're not moving at relativistic speeds. And then the dark energy, which was discovered fairly recently and is responsible for the fact that the universe is undergoing an accelerated expansion. The rate at which it's expanding is actually accelerating at the current time.
Excuse me, Stephen.
Yeah.
One of the guesses about what cold dark matter, well, what dark matter might be, not necessarily cold, would be not neutral, sterile neutrinos, which would be quite heavy. Would they also be nearly at the speed of light because they're heavy, or would
No.
they be much slower?
They'd be much slower. Whether a particle moves close to the speed of light or at the speed of light, or whether these particles are cold. Now, cold means that they're moving much, much more slowly than the speed of light, which means that their energy density mainly resides in their mass. That's really what the term cold dark matter means. It means that the energy that these particles contribute to the overall energy in the universe is in their rest mass energy. So massive neutrinos would pretty much behave the same as, say, electrons. As the universe expands and the temperature goes down, these massive particles would become non-relativistic much earlier than particles that had very small rest masses. So that at the present epoch, massive particles would be non-relativistic now. But particles like neutrinos, which have minute, as far as we can tell, rest masses, might still be moving at close to the speed of light.
Thanks.
Yeah. Anyway, there is a currently favored model, which is called the lambda CDM model, random cold dark matter model, which is a cocktail containing a critical density of about 5% ordinary matter, 25% cold dark matter, and 75% dark energy. These numbers aren't quite the ones that people are converging on, but they're close. Good way to remember them anyway. So most of it, obviously, most of the stuff in the universe is something that we don't know much about. We only know much about that 5%. So that's, again, a very broad brush cosmological picture. And let's take a look at what the status of cosmology was in the late 50s, early 60s, when I was going through college and getting into graduate school. Well, we didn't really know much about anything in the universe. There were two basic models of the universe. One was based on the so-called cosmological principle. The universe is homogeneous and isotropic, and because it's expanding, And if you extrapolate backwards, it was smaller um, and presumably hotter. Uh, you sort of have a Big Bang theory where the universe started out being very hot, dense, and that um, picture of the universe was first really seriously enunciated by Alfred Gamow and Herman in several very, very good papers that were written in the 1940s, but then subsequently completely forgotten. And some other astronomers, astrophysicist Burbage, the two Burbages, and the Russian Zeldovich, um, sort of were leaning towards the Big Bang theory. Burbage, Fowler, and Hoyle, these two authors, there's four authors, I should say, wrote a seminal paper about how elements get produced inside stars. The one problem was they couldn't account for the abundance of helium. Helium is much too abundant that you could not create it's about 25% by mass in the universe. And you can't manufacture that in stars. So they looked at the possibility of manufacturing it in early stages of the Big Bang. But they were mainly interested in stellar processes. And there was an alternative picture of the universe, which was based on the so-called perfect cosmological principle, that the universe is homogeneous and isotropic, like the cosmological principle. But in addition, it was time independent. So to reconcile with the fact that the universe is expanding, they had to postulate that matter was being continuously created to make up for the fact that it was being diluted by the expansion. You didn't have to create very much of it, maybe a few particles of hydrogen in a cubic meter every billion years or so. But that's what it took. So-called steady state theory. So we had the Big Bang theory and the steady state theory. The Hubble constant was somewhere between 50 and 100. Dark matter and dark energy had yet to be discovered, as well as the cosmic background radiation, cosmic microwave background radiation. So that's where we were in the late 50s. And as I state at the bottom of this slide here, could equally well be taught in the philosophy course for all that we knew about it at that time. But things radically changed in 1964 and 1965 with the discovery of cosmic background radiation. And this was a remarkable example of serendipity. Penzias and Wilson were working on a completely different project involving this large horn antenna. They were examining the possibility of bouncing microwaves off a big balloon called ECHO in the upper atmosphere. I think it was either in the upper atmosphere or it was actually a satellite. I can't remember which one. But they were plagued by noise in the antenna that they couldn't account for, some hiss that was there no matter where they pointed this antenna. And they spent about a year trying to eliminate it. Finally, Penzias, in a conversation with a colleague at MIT, talked about this problem. And this colleague had a friend, another colleague, who had attended a seminar given by Jim Peebles. Now, Jim Peebles was a member of a Princeton group organized by Robert Dicke. He hired Jim Peebles, a theorist, and Roland Wilkinson, who were experimentalists, to see if they could detect this cosmic background, microwave background, I'll just call it CMB, radiation, which Dicke had suggested might be there as a consequence of the early stages of the universe where helium was being produced. He had Peebles, the theorist, recalculate the expected abundance of helium if the universe had gone through this very hot early stage. And he and his two other students were tramping around the top of the physics building in Princeton, assembling an antenna. Well, anyway, Penzias's colleague alerted him about this group, and they made a phone call. And Dicke picked up the phone and heard about the problem that these two guys were having with this antenna, said they'd come out and take a look, hung up, and looked at his fellows and said, "We've been scooped." And that was a real scoop, because had they been allowed to finish their research, they would have undoubtedly gotten the Nobel Prize. But anyway, they met with Penzias and Wilson, and they finally agreed that what they were looking at was indeed the CMB. Now, to make clear what that is, think about the early universe as we extrapolate the universe backwards in time. The radiation that fills the universe at present, the CMB radiation, as the universe got smaller and smaller, would get hotter and hotter. At some point, it would exceed about 3,000 degrees Kelvin, at which point the hydrogen in the universe would become ionized and would interact strongly with photons via photon-electron scattering. The electrons would be free, so you have what's called Thomson scattering at low energies, and my mind's going blank. Thomson and, well, I can't think of the other name at the moment, but these would cause photons to, or restrict photons to only travel a very short distance before being scattered. So they become tightly coupled with the electrons, and the electrons would be tightly coupled to the protons via electromagnetism. So you had a baryon photon gas that was tightly coupled. The photons weren't going anywhere. And this green dot is, let's say it's the Earth. Now, of course, the Earth wasn't there at the time, but let's put it there just for the sake of argument. As the universe expanded and the temperature declined, at some point, the temperature would pass through about 3,000 degrees Kelvin, and as it decreased beyond that point, the electrons would combine with the hydrogen ions, become neutral hydrogen, so you don't have any electrons, don't have any free electrons anymore. And the interaction of photons with hydrogen atoms is much, much less. Neutral hydrogen atoms is much less than it is with free electrons. So all of a sudden, the universe became transparent to photons. So the photons started streaming. And a little later, say not too much, the photons, each photon could travel so far, as indicated by the length of the arrow. And the photons that were arriving at the Earth at that time would have come from this dotted circle. Actually, think of a sphere, if this were 3 dimensions. Photons coming from the surface of that sphere directed towards the Earth would be hitting the Earth at that time. And the farthest anybody on Earth at that time could see would be the surface of that sphere. Outside that, photons haven't had time to reach the Earth, so that part of the universe would be unobservable at that time. Well, much
Steve,
later, yeah.
Most people, when they see or think about a picture like this, they think about it as the Earth or whatever that point is as being the center in some sense. But what you're talking about is actually every point in the universe.
Exactly.
Can you explain that for people, because it's a hard concept for most people to get?
Exactly. You could put this green circle anywhere in that picture and draw the same diagram, and you have the same situation. That's just a reflection that the universe appears to be homogeneous and isotropic. It's the same everywhere and the same in every direction. So where that green circle is and that dash circle is completely arbitrary. Put it anywhere and you get the same picture. That's a good point. Thanks.
No problem.
Later on, let's say today, the photons would have had a chance to travel much farther, and we'd have this situation here. Again, you can put that green dot anywhere. It's arbitrary. But now what's hitting the Earth are photons that have emanated from this much larger circle or sphere, if you think of it in 3 dimensions. That's the CMB. These are the photons that have originated from this dashed line circle and of just arriving at the Earth today. They left that dashed circle when the universe was getting cooler than 3,000 degrees, became transparent, and the photons started flying in every direction. And now they've just photons that happen to have left the that dashed sphere directed towards the Earth are arriving at the Earth.
That time was roughly about what, 3.74 million years after the Big Bang?
It became transparent. I think the currently accepted number is about 380,000 years.
Oh, 1,000, not, yeah, okay, sorry.
Yeah, 380,000 years.
Okay.
About a third of a million years.
Yeah.
So, of course, in the meantime, the universe is expanding all the time. So these photons are coming towards the Earth, but the universe is expanding. And that causes the photons to be redshifted. Okay. So what were photons that were emitted from a soup of photons and 3 electrons and hydrogen ions at 3,000 degrees? If you happen to put yourself back at that time, it would be like looking like you being somewhere in the sun. Everywhere you look, you'd see this blinding light. At 3,000 degrees, it's very, very, very bright and in the visible. And then these photons, as they propagate thanks to the expansion of the universe, get redshifted more and more. And by the time they reach the Earth, they've been redshifted into the microwaves. Well, this was a real transition. And the first object in the study of this CMB that was discovered by Penzias and Wilson was to ascertain whether or not it was black body radiation. So to do that, the COBE satellite, Cosmic Background Explorer, was proposed, I think, in 1977 and actually launched in 10, 11 years later with a mission of determining the temperature of the CMB, or whether or not the CMB was black body and could be characterized by a temperature, and then to see if there were any anisotropies in the temperature of this CMB. So the CMB, when observed at a 1 in 1,000 degree resolution, was found to be completely uniform in all directions. By the way, this presented a problem, and I'll just briefly mention it because that deserves a whole nother presentation. But 2 points on this, according to the standard Big Bang theory, 2 points on this, this is sort of a all sky view of the CMB. And 2 points on that all sky view separated by more than about a degree, well, 2 degrees actually, could never have been in causal contact according to the standard Big Bang theory. So it's a mystery why they're at the same temperature. How did one part know what the other part was doing? And that problem was addressed, as well as several other problems, by the theory of inflation, the fact that the universe went into a very, very, very rapid phase of expansion very early in its history and sort of set the initial conditions of the Big Bang. So I mentioned that, but that's all I want to say about inflation at this point. So again,
the only thing I would comment is that inflation, although it solves all the problems, is 2 problems. The first is there's absolutely no evidence for it, physical evidence, no experiments. And secondly, there's a lot of things that are put in by hand in the theory. So it's not quite a great solution, at least in my mind.
well, it does several things very nicely, which makes it compelling.
Oh, I absolutely agree. It solves everything, but it is a fix. It's a fudge.
Well, I can't disagree. It's very compelling, but as you say, the mechanism is entirely made up. It's not.
Okay, well, thanks. I just wanted to point that out because a lot of people seem to think that it's actually, been measured or something like that.
Right. Good point. Good point. No, it's very much a theory. Okay. Just to remind you what black body radiation is and what and how it's characterized, black body, the name black body radiation got that name from the fact that it's the kind of radiation that would be emitted from an object that was completely black. So if you had an object that was able to 100% efficiently absorb visible light when it was cold, when you heated it up to say 4,000 degrees Kelvin, it would glow and it would emit radiation with what's called a black body spectrum. It's the kind of radiation that you would find if you were to take, for example, a box with a fixed temperature of the walls of the box and radiation inside. Now, what would happen would be if you think of photons in that radiation at any particular frequency, some of those photons will be absorbed by the walls of the box. Some of the photons will be created and emitted by the walls. And this will go on until you reach the steady state, where as many photons of a given wavelength or frequency were being absorbed as were being emitted. And this would hold true if you waited long enough at each wavelength. Well, when this was all done, you waited long enough, the radiation inside of the box would be completely equilibrated with the walls. And the spectrum of that radiation would be a universal black body spectrum characterized solely by the temperature of the walls, or of the radiation itself. You could characterize it by a temperature because there would be a unique relationship between the temperature and the spectrum of that radiation. Spectrum would depend only on the temperature and nothing else. And this is what the spectra look like at various temperatures. You can see that as you increase the temperature, the amount of radiation that you would have would increase quite dramatically. Actually, it goes as the temperature to the fourth power. And then the peak of the spectra would shift to shorter wavelengths. So at 3000 K, the shift is kind of, the peak is in the red. At 7000 K, it's way over towards the blue. At 6000 K, which is what the temperature of the sun is, the sun's a pretty good black body, by the way. If you cooled the sun, it would look quite black. It would absorb most of the radiation that impinged on it. So when its temperature is the present value of 6000 K, it radiates a spectrum that's close to being black body. As you can see, it peaks kind of in the green-blue. Now, when you look at the sun through appropriate filter, it doesn't look bluish. It looks more yellowish or whitish. And that's because a lot of the blue light gets scattered in the upper atmosphere. It gives us our blue sky. And then what comes directly at the sun has been that the blue component has been partially subtracted. Anyway, that's black body radiation. Again, it's a spectrum that's characterized entirely by the temperature, nothing else. Well, Kobe measured the spectrum of the CMB. As you can see here, it's essentially a perfect black body spectrum. It's about as close to a black body spectrum as anything we've ever encountered. So that tells us something very interesting. Sometime in the past, this radiation must have equilibrated with matter. And then as the universe expands, the photons, once they decouple from matter, stream freely. They retain this black body spectrum, which they must have acquired when they were closely coupled with a matter and could interact with it and achieve an equilibrium. As the universe expands and the wavelengths get redshifted, the black body nature of the spectrum doesn't change. It retains its black body character, although characterized by a lower and lower temperature. So nowadays, what the spectrum of the black body radiation with the CMB, it has a peak wavelength of about a millimeter, a little over a millimeter. And you can compare that with the microwaves of a microwave oven, where the microwaves have a band around 12.2 centimeters. So this CMB has characterized by wavelengths that are somewhat shorter than what you'd find in a microwave oven by actually a factor of about 100, but we're still talking microwaves. And the temperature of this spectra turns out to be, you can fit that spectra with a black body spectrum characterized by a temperature of 2.728 degrees. Any other temperature doesn't fit the observations. So that tells us when you characterize electromagnetic radiation by a temperature, you're talking black body radiation with a spectra that's characterized at that temperature. Now I'm going to display a couple of simple formulas here that I'll just, there's one or two points I want to bring out, which is all I'm interested in here. But as the universe expands, as you can see in the upper right here, the wavelengths of photons propagating through the universe increase. We say these photons become redshifted. Well, that's what's happened to the CMB as the photons propagated through the universe. The expansion of the universe redshifted these photons. So the spectrum went from a spectrum of 3,000 degrees when it decoupled from the matter to the present value of about 2.728 degrees today. And this just tells you, these formula tells you quantitatively how that happened. A few times I will refer to, once or twice maybe, talk about the redshift parameter Z, and that just refers to the observed wavelength of a photon minus the wavelength it had when it was emitted over what it was when it was emitted. So it's a redshift factor, it tells you how much the photon was redshifted. Okay, and 1 plus Z, when you study a little cosmology, you learn that the observed wavelength over the emitted wavelength. So you think about a photon emitted sometime in the past, it propagates through the universe, and you observe it today. Well, the redshift of that photon, how much the wavelength has been stretched, is proportional to the size of the universe today compared to the size of the universe when it was emitted. And you have to be careful when you say the size of the universe. Well, what do you mean by that? Well, think about the distance between two clusters of galaxies. Now that has been increasing in time as it takes part in universe expansion. So you can sort of characterize but the size of the universe today compared with the size of the universe at some time in the past by how much the distance between these two clusters of galaxies has increased during that time. Okay, And that's just proportional to, again, if we're talking black body radiation, the size of the universe today divided by the size of the universe sometime in the past is equal to the ratio of the temperature of the emitted radiation to the temperature of the observed radiation. Okay, so that's a very simple relationship. Tells you that the temperature of the radiation just scales inversely with the size of the universe. So Z at recombination was equal to the 1 plus Z at recombination or a decoupling. You're describing the same thing by those two terms. Recombination refers to when the electrons combined with hydrogen and the universe became transparent. And decoupling just describes the fact that at that time, the photons decoupled from the matter and went off freely. And that's just the ratio of the temperature at recombination, which was 3000 K, to the temperature today, which was 2.728. So that was that 1 plus the redshift factor was about 1100, which means that the universe at recombination was about 1100 times smaller than it is today. Okay. So if we subtract out the uniform 2.728 black body energy, radiation energy, we're not left with nothing. There's actually some structure there left over. That is part of the all sky view. Part of the radiation had a temperature slightly less than 2.728, and another part, the red part, had a temperature slightly greater than 2.728. It wasn't completely uniform. And this is the so-called CMB dipole. And what it is due to is the fact that the Earth seems to be moving through the rest frame of the CMB. So we're moving into, the photons that we're moving into get slightly blue shifted, and the photons that have to catch up are slightly redshift. It's a Doppler effect, okay? And so this indicates our motion relative to the rest frame of the CMB. And that's due to a lot of things. The Earth rotates, it orbits about the sun, as you can see in that tilted circle there. In the meantime, the sun is orbiting around the galaxy with a speed of about 230 kilometers per second. So that gets combined with the speed of 30 kilometers per second of the Earth's orbit about the sun in a way which depends on the two different directions. And the sun is, again, it's moving around the galaxy at about 230 kilometers per second. And the whole galaxy is drifting towards a constellation. I think it's in the constellation Hydra, near there, I'm not sure. But that, the drift of the galaxy is about 600 kilometers per second. And when you add up all these velocities, the velocity of the Earth relative to the CMB turns out to be about 400 kilometers per second. So that accounts for that dipole. So you have to, if you want to see any further structure, if there is any, then you have to subtract this dipole component, which is mainly a Doppler effect due to the Earth's motion. Well, if you subtract that out, then um, you'll see structure. It's not completely uniform. This was the first indication, this was the other mission of the COBE satellite, was to see if they could detect any structure in the CMB once you subtracted out the uniform part and the dipole part, anything left over. And apparently there is. And you have to look at it with a resolution of 1 in 100,000. So we're looking at a change in temperature. If you look at the upper left there, what we're looking at in these diagrams, these all sky diagrams, is a difference in temperature from the average. The average is 2.728 degrees. And then the actual temperature at a particular point in the sky, minus the average temperature, is what that delta T is. And we're talking about a difference in 100,000ths of a degree. Okay, that's the kind of differences we're talking about. But they're there. And the fascinating thing about that is that it explains, or one would hope anyway, when one got a much better, higher resolution picture of that, that would explain the origin of structure in the universe. Where did the galaxies come from? If everything were completely uniform, it would remain uniform. There wouldn't be any tendency for parts of it to contract and other parts to become rarefied. So there had to be initial irregularities in order for structure to form. And these irregularities were another prediction of inflation. So it's another feather in the cap of inflation, even though we don't know the mechanism of inflation, as Bob pointed out. But it does indeed explain these variations that ultimately due to quantum fluctuations when the universe was coming out of its inflationary epoch, and different parts were coming out at very slightly different times and laying down this structure. Well, we'll come back to this because this is essential to the Hubble constant. You may remember that we're talking about the Hubble constant at some point, and we'll get back to it, but all this is a part of the story. So the structure, this is a crude analogy and not a very good one, but I'll give it anyway. If you think about, this looks like a pond, and you're putting, all of a sudden you put you've thrown a bunch of pebbles in this pond, and the waves are propagating out. If these were sound waves, you think about them propagating out in 3 dimensions. But the important point is that this mechanism, and I'll come back to this mechanism a little later in more detail, but it lays out a structure with a scale, a large scale whose actual physical distance we can compute. You think of that horizontal white line there, sort of marking out the distance of the crest from the center. Well, that's a dominant component of the distance scale of the structure. And we can, again, from the fact that we know how long it took from the Big Bang to the decoupling point of the universe, when the radiation decoupled from the matter. Prior to that point, the baryons, and I'm going to call them baryons now because I want to distinguish them from the dark matter. The baryons are the neutrons and protons, the ordinary matter. So when I say baryons, I'm talking about ordinary matter. These were coupled tightly with the radiation before decoupling, and they acted like a gas, in the sense that if you compressed it a little bit, it would, you take a balloon of gas and compress it, it'll rebound. Well, that was the way this coupled baryon and radiation gas behaved. If you perturb it, it would respond and probably oscillate back and forth. But we could compute, because we know the time at which the decoupling took place. We could compute that from the temperature and the way the universe was expanding at that time, given its contents. We could compute the velocity of sound and how long that sound propagated, and therefore how far the sound propagated from to the time of decoupling. Well, that sets a scale. So that's a very important scale. We know what it is. So I'm going to be coming back to that shortly. Well, to improve the resolution and perhaps get some information about parameters in the universe, two experiments were launched from the Earth, so-called the Boomerang experiment and the Maxima experiment. There was the third one, the Daisy experiment. These were attempts to observe the CMB with a high resolution, much higher than the Kobe satellite was able to manage. But only for a small part of the sky. They couldn't do all sky surveys. One was launched from the South Pole, the Boomerang, and one was launched from Maxima. The balloons went up about 40,000 meters up above most of the atmosphere, so they could examine the CMB without any atmospheric interference. And they were able to ascertain that the universe was flat to good approximation, and that the baryon content was about, they could determine that to about 4%. So how is that done? How is the universe ascertained to be flat from that CMB structure? Well, the argument is as follows. Here are three different examples of possible examples of how photons could propagate to us from each side of a structure whose diameter we know. So we can compute the width of that horizontal bar, say. We know physically, we can compute physically how big it is. We can also, knowing how far it is away, and this depends somewhat on the model that we have of the universe. So all of these arguments have to be sort of self-consistent with other data and so forth. We know, so suppose we know physically the width of that bar. We know how far it is away. Then the angle that it subtends in the sky would depend on the geometry of the universe. If you take a look at the situation on the left, we're talking about a positively curved universe, and the photons, which propagate along geodesics in that space-time, would follow those curves that are drawn there, and would arrive at the Earth, each, one from one side, one from the other side, and they would appear to subtend a larger angle than would be the case if space were flat, which would be the case in the middle. And if we were in a negatively curved universe, the subtended angle would be smaller than what you'd compute if you were in flat space. So if you knew, again, physically, what the width of that bar was and how far you were away, observed the angle from one side to the other, you could tell whether or not space was flat or curved and which way it was curved. Well, that's the kind of argument that goes on when we talk about the geometry of space and how it's determined from these CMB observations. More technically, if you look at what goes on as the universe expands, in the case of flat space, you see that what starts out at the upper left grows as the photons propagate towards the Earth, and eventually it's quite much, well, it's 1,100 times larger when it reaches the Earth, but the angles don't change. Everything's sort of conformal. It just gets larger. But that's sort of what it might look like in a bit more detail. And the spectrum that, for example, I think I have it here on this slide here. Boomerang and Maxima and Desai were able, because of their high resolution, were able to obtain the angular structure to a fair approximation of the cosmic microwave background radiation. Well, okay, what do we mean by the angular structure? Firstly, if we look at the abscissa, we're listing the multipole. And what we're essentially doing is the following. I'm going to go back to maybe this slide here. You pick a point, let's say a point, one of those blue sections, maybe in the upper left. You pick a point in that blue section, and then you pick a given angle, which corresponds to how far away an angle from that point you're going to consider. So you pick a point like that, one of those blue splotches, and you pick an angle, say 3 degrees. So you're going to look 3 degrees away from that point in different directions and see if you see something other than the average temperature. Then you're going to go 4 degrees and see if you see anything beyond the average temperature. Maybe you see a higher temperature on the average. Then you go 5 degrees, see if you see anything other than the average temperature as you look in different directions. And then you pick another point and do the same thing. So if everything were at a uniform temperature, then it wouldn't make any difference where you picked your initial point and how far an angle you look from that point. You'd see the same thing. But if you have structure, you might see more differences at 3 degrees. If you went 3 degrees from an arbitrary point, you might see more structure having the same difference in temperature as was at your point. than you would on the average. So so that tells you that there's some kind of correlation between an arbitrary point and a point, say, 3 degrees away. If I pick a point with a blue splotch, then I'm more likely to see another blue splotch at 3 degrees than not. If I pick a point 5 degrees, maybe I don't see anything on average. And that's what's going on with this diagram here. These are called multipoles, and they're sort of inverse to degrees. As you can see, I've indicated that on the just below the diagram here. The multipole L, that's a technical term as to how these angular arguments are done mathematically, but they're essentially inverse degrees. A given L is, you can think of it as 180 divided by theta degree. So for example, 200, L equal 200 is about 1 degree. It's a little greater than one degree. Yeah. No, I'm sorry, a little less than 1 degree. And as you go to higher multipliers, you're talking about smaller and smaller degrees. Well, of course, Kobe wasn't able to resolve the structure at the degree and the fraction of a degree level of resolution, but Boomerang and Maxima Desai were able to. And this peak, this first peak, indicates it's the angular size of this thing. That first peak, where it is, tells you what that angle, those two propagating photons meet at. Okay. So if that peak, say, were to the left of where it actually is, that would indicate a closed uniform universe. If the peak were to the right, that would indicate an open universe. But the actual peak lies within less than 1% to what that angle would be if the universe were flat. And that was the main result of these ground-based experiments. They also were able to estimate the baryon content of the universe. And that has to do, and I'll explain how that's done a little later, but it has to do with the difference in height between the first and the second peak. Second peak is not very well defined there in these experiments. So that's where we stood until these new, more sophisticated experiments were done. The WMAP, which took data from 2001 to 2004. These were actual satellites. And the European Union Planck satellite, which took data from 2001 to 2013. And these were specifically designed to probe the microwave background anisotropy with much more resolution than Kobe was able to do initially. And from that, one should be able to, or one would be able to ascertain many of the parameters of the universe, basically what's in it, what's in the universe. And again, to what degree the universe is flat. Stuck in all of that, and it'll become again apparent later on, is the Hubble constant, which again, we're ultimately interested in. Well, these satellites were sent out to the so-called L2 Lagrangian point, which is in a direction opposite the direction of the sun. And it's a point, if you put an object there and have it orbit at the appropriate speed, it sort of stays locked in that position. It continues to be directly behind the Earth relative to the sun as the Earth orbits about the sun. But it's an unstable position. You have to keep giving it slight corrections to keep it there. And it didn't occupy just a point at L2. It sort of went into a elliptical orbit above and below L2, just so that it could examine the sky near the sun. If it were at L2 exactly, it would never be able to probe the sky in the direction of the Earth and the sun. But being sometimes above and sometimes below the plane of the orbit of the Earth, it could peek at the sky that was directly behind the sun if it were just at that L2 point. They each carried this a collection of differential radiometers, which were pointed at different directions in the sky and determined very precisely the difference in the radiation energy and therefore the temperature of the radiation, these two different directions. And as the satellite slowly rotated and orbited about the sun, they were able to do a complete sky scan. And from these differences in temperatures, we're able to construct a map of the structure of the CMB. What they would get would be what you see here, much higher resolution. You're seeing the structure at much higher resolution, but you also see this red foreground emission that's due to the galaxy. And by probing it at different wavelengths, you get a much better handle on what that galactic spectra of the galactic emission and can subtract it out. A lot of painstaking work, and you get these all sky pictures. This compares the Kobe 1992 experiment with a WMAP and ultimately the Planck. The Planck gave us the highest resolution of the CMB anisotropes. And that allowed us to get a very detailed angular spectra of the structure of that CMB. And again, what we're looking at is structure at various angular scales. Again, what that structure means, let's say you take the thing at just about 1 degree there. If you take a 1 degree, take 2 points and the CMB separated by 1 degree, you're more likely to find those 2 points that the CMB is correlated, that if it's slightly hotter at the first point, on the average, it's going to be a little slightly hotter at the second point, compared to what it would be if the thing was completely random. That's what that is. At very large angles, you can't get much better resolution than is indicated by the error bars there, simply because there's just too few samples. At large angular scales, there's just not that much independent observations. So there's this unavoidable statistical variance that is going to occur. Well, this structure tells us an awful lot about the contents of the universe. And I'll try and explain one of these. It's all kind of complicated because there's a lot going on. But here's an example of simulations that were done to compare with the spectrum as determined by, I don't remember, I think this is, this may be WMAP, which it has these red red dots with angular error bars that sort of, there's a solid line that matches those quite well. And then there's dash dot line and dashed lines and a dotted line, which don't match it well at all. Well, these dashed and dotted lines refer to what you would expect if the baryon concentration in the universe were greater or less than about 5%, 4.6% to be exact. So what you're seeing is a so-called baryon drag peak in the first peak. And then the second peak looks like it's either sort of unchanged or it's maybe even a little depressed from what it would be with other, if you were, say, to assume that the universe had a greater percentage of baryons than, say, 4.6%, then the first peak would be high. The difference between the first peak and the second peak would be greater than you experimentally determined. And if the baryon concentration were smaller, then the first peak, the difference between the height of the first peak and the second peak would be smaller. So by comparing these simulations with the data from WMAP or from Planck, you get a very, by fitting the data, you can get a very precise indicator of what, in this case, what the baryon concentration is.
Steve,
yeah.
I just want to comment that if you do the same thing for different kinds of models for gravity other than Einstein's general relativity, the peak of the third relative to the first almost always doesn't work with any of the other types, Tevis or any of the other kinds of alternative thoughts of what general relativity might be. And it's a really interesting result that not only can you, determine various kinds of measurements of the baryon, you can also check against these various alternative theories of Einstein's theory of general relativity.
Oh, well, that's very interesting. And I presume these different theories were concocted, at least in part, to try and explain away dark matter.
Yeah.
Yeah. You perceive the presence of dark matter in galaxies by the fact that spiral galaxies, for example, rotate a lot faster than they would if the only matter present were what you could see as luminous matter. And the gravitating force of this luminous matter would not keep these outlying objects in orbit. They'd be flying away. The gravitational pull of the luminous matter is just not enough to keep these objects in orbit. You need a lot more matter there, and presumably that's what the dark matter.
Right. So it's the peak between the first and the third that almost always is the argument that it has to be dark matter as opposed to a different theory of relativity.
Oh, thank you. That's really interesting. That's very important.
Yeah.
Some of these parameters, like the baryon density in the universe, have independent checks. Here's one of them. With Big Bang nucleosynthesis, that orange line, which is steeply descending from left to right, is the deuterium abundance you produce, depending on the baryon density in the universe. The scale on the bottom is the baryon density. You run through these computer calculations, assuming different baryon densities and seeing what you make as the universe cools. When it reaches about 10, anywhere from 10 billion to billion degrees, that's when all this nuclear synthesis takes place. You produce the helium. But the lithium, not the lithium, but the deuterium, you can see, is a very sensitive indicator of the density of baryons in the universe. The trick there is to measure the deuterium. And that's tricky because stars tend to consume it when they form. So deuterium tends to be depleted. So you have to look at very, very old, high redshifted gas clouds and take the spectra of these and determine the deuterium abundance from the slightly different spectra they produce than hydrogen. And you get this sort of this gray vertical stripe. That's the deuterium abundance that you measure puts the baryon density within that gray stripe. So that's an independent check on the CMB results. So what's going on? And this is a very complicated thing, and I think I can capture a bit of it in this argument I'm going to produce. Why does the baryon number change the structure of that peak, the first peak and the second peak and so on? So we're going to think about a rubber band that if you were to let it just hang there, it might assume something like the shape of the lower left, maybe not quite as deep as that, but it would, it would be technically, what would that be? A catenoid or something like that. Anyway, let's just say that initially it was horizontal. So if it were allowed to do its thing, it would start falling. Okay. And if it overshot its equilibrium position, it would rebound and come back to the horizontal and then go back and forth. Well, the inflation, if it, whatever, seemed to lay down inhomogeneities, which we observe in the CMB, but inhomogeneities in the matter distribution, these very slight inhomogeneities, which get inflated to very, very, very large scales, way beyond, most of them way beyond the sonic scale, the scale, or even the scale, trying to think of the term, um, the causal scale. They get so large that parts of them are completely outside the causal length of other parts. So they'd be way beyond our observable universe, these fluctuations, but some of them would be small. Now, as the Big Bang commences, the sonic scale, now this is sound waves that are propagating out from inhomogeneity. So you have a slightly over dense or over pressure region and an under pressure region next to it. Well, once they become in sonic contact with each other, once they know each other is there, they can begin to equilibrate. They can begin to undergo oscillations. Now this sonic length is continually increasing as time goes on until decoupling. When decoupling occurs, then this coupled baryon radiation soup no longer can propagate sound waves. So let's say you didn't have any baryons, then that first peak would be produced when the sonic wave got large enough so that inhomogeneities equal to that sonic length began to feel each other and began to evolve. Okay. Well, in the case of the rubber band here, just at the right instant before decoupling, this rubber band, this rubber band representing an inhomogeneity began to respond. And it responded such that it, gravity, there's a little extra gravity, pulled it down, as you can see in the diagram at the lower left. And it occurred just at the right time before decoupling, so that when decoupling occurred, it was at its maximum depression. So we got a structure there that about the largest structure you could have as the universe evolves. Now, if you instead put some beads on that rubber band, and if this density inhomogeneity also produced a little gravity, so everything was being pulled in, what would happen now if you started out with the initial state indicated in the upper right, then all those that had a structure about the right size, by the time the sonic length reached that structure, they would start to evolve. And if the timing were right, they would reach their maximum, this rubber band would reach its maximum depression at the time of decoupling. And you can see that the presence of the baryons causes the rubber band to be stretched further than it would have been stretched if the beads weren't there. Well, the beads represent the baryons that are coupled to the radiation. And this so-called baryon load causes the compressions of the density inhomogeneities to go beyond what they would be, sort of inertial effect, go beyond what they would be if the baryons weren't there. And that causes the peak of that first, that structural peak to become more pronounced. If you, so the argument I just gave applies to the left. You got to think about the sonic distance continually to increase. And again, everything depends on timing. Those inhomogeneities that happen to be at the largest scale before decoupling, such that when decoupling occurs, they achieve their maximum compression. Those are the regions that constitute the first peak. Now, smaller regions, if they, for example, when the sonic distance was smaller, well, homogeneities on that scale would begin to evolve when the sonic region exceeded their typical scale length. And they would evolve faster. And one that happened to be just the right scale would undergo a complete oscillation by the time decoupling occurred. And that would constitute, those would produce the second peak. And so the argument is somewhat like that. The greater the baryon load, the first peak is highly influenced by it, because that on that large angular scale, when decoupling occurs, they're at their maximum compression. This second peak is produced by those inhomogeneities that happen to be released on a smaller scale at such a time that they went through a complete oscillation, and at the time of decoupling, they were back to their initial state. But coming back to their initial state, even though they were baryon loaded, they didn't reap the rewards of having that baryon load. In other words, coming back to their initial state wasn't affected by the baryon load. So that second peak wasn't really influenced much. So the difference in height between the first and the second peak was a measure of the baryon load. That's about as best as I could come up with in an argument to try and explain where this structure came from. Anyway.
Can I ask just a quick question?
Sure.
What is the significance of the distance between the first and second peak and the second and the third peak? What kind of information can you gain from that?
Okay. The third peak turns out to be more of a indicator of the dark matter. In fact, this next slide here shows you I really can't go much beyond these pictures here, because again, scenario becomes a little complicated. You've got photons that are climbing out of gravitational potentials and being redshifted. On the other hand, some photon compression heats up and causes the photons to be more shifted towards the blue because the temperature is increased. So you have a lot of effects going on, and it's hard to disentangle everything. But the kind of differences you get in this structure by varying various components is shown here. At the top left is shown the curvature. Now, remember that we argued that the universe was flat, and that was based on the, if I come back to it, the long way, that was based on where that peak was in angular scale, how far it was from the left or the right of that diagram. And so you can see in this picture on the upper left how that peak is shifting left and right depending on what the curvature. Now, curvature depends again on the total energy density in the universe. Okay, there's a critical energy density at which the universe is flat. Now, the position of the first peak is a geometrical argument for whether the universe is flat or curved, because it tells you that angle between each side of a structure whose physical length you know. And varying the energy density of the universe, that sigma tot at the bottom, what it is equivalent to varying the curvature of the universe from positively curved, from flat to negatively curved. And that again just displaces the peak horizontally. So where the peak is horizontally is basically telling you the geometry of the universe. And then the baryon load, the lower left, you vary that, and you get these different possibilities, which you compare with the observations. And on the lower right, you vary the dark energy, and you get these different possibilities, again, which you would have to compare with experiments. So it's kind of, you're fitting all these parameters to the spectrum that you get with from these experiments. The very large scale structure on the left of all these diagrams is basically structure that was imprinted by inflation or whatever that gave us the initial asymmetries to begin with, anisotropies to begin with. They have not had time to evolve. They are too large. They lie out of the sonic scale, so they have not evolved. At the right, as we go towards the right, the peaks get more and more, less and less pronounced, I should say. They sort of get washed out as you go further and further to the right. And that's due to an effect called silk damping, named after the astrophysicist who first explored this. And what it has to do, as these angular structure gets smaller and smaller, physically you're talking about parts of the inhomogeneous that are closer and closer to each other. So you might have an underdense region very close to an overdense region. And if they're close enough, photons have basically a chance to random walk between the two, and it tends to wash out the contrast between the two. So at very high angular resolutions, a very large L, very small angles, you're seeing the structure washed out. So again, by curve fitting these different choices for the parameters of the universe, you can find a set of parameters that best fits the structure of this this angular structure of the CMB. And at the bottom, you'll see somewhere in this fitting is the Hubble constant, this omega b h squared. Omega b is a measure of the baryon fraction in the universe, but the h squared is the Hubble constant in units of 100 megaparsecs per 100 kilometers per second per megaparsec. It's the fraction of the actual Hubble constant to 100 kilometers per second per megaparsec. So part of that fitting is requires tuning the Hubble constant. But there's a really powerful argument for what the Hubble constant is based on cosmology, which in part depends on this because this sets the parameters of the model, namely the lambda cold dark matter model. The parameters that model are pretty much set by these, by the structure. And well, this just shows you what the structure appeared to be at decoupling 13.7 billion years ago. Is the bottom one. The thing that's obvious is that the dark energy is not there, or at least it's there, but you can't see it. It's too small. But as the universe expands, the dark energy becomes more and more important, becomes a greater fraction of the energy density of the universe because the other contributions to the energy density get diluted, whereas the dark energy doesn't. It stays the same per unit volume, assuming it's due to a cosmological constant or to a field that has a particular equation of state that resembles what a cosmological constant would have. Anyway, here's some, I don't want to scare anybody by these formulas here, but I just want to point out several things. Knowing omega m, which is the matter content of the universe, the cold dark matter plus baryons, and knowing omega r, which the radiation content of the universe is, which is not very important now, it's been diluted out, and the dark energy, which is the omega, I'm looking at the second formula. Okay, so that's the content of the universe. And Z is the redshift parameter. The greater Z is, the further back you're going into the universe's past history. Well, the right-hand side of that formula tells you what the Hubble constant is as a function of the redshift parameter. If Z is 0, that gives us the present time. And all of the stuff in the square root sign adds up to 1. So the Hubble constant at Z equals 0 is just equal to the H naught, the Hubble constant at the present time. Well, you plug that into the formula at the top, and you get what's called the angular distance. Okay, so the only lesson I want from these set of formulas is the fact that given the lambda cold dark matter model of the universe, which sets these parameters, we can compute hz and we compute the angular distance. The angular distance, by the way, is shown at the lower right. D sub m is equal to the physical width of the object divided by the angle that it appears in the sky. So if we hop back to this thing again, it's the, if you know the width of that bar and you know how far it is away, you can compute the angle. What the angle should be, say, in flat space. Now we can turn that around a little bit and say, if we know what the physical diameter or length of that bar is, we also know what the angle is. We can observe the angle. Then we can compute the angular distance. It's just the width of that bar divided by the angle, if you measure that angle in radians. So it's a very simple formula. And we can compute what the angular diameter should be at any given redshift if our model is correct and if the Hubble constant is what we think it is. Or, turning it around, if we compute the angular distance from that formula and compare it with the angular distance of some structure that we observe, whose actual physical diameter we know, and whose actual angle it's subtended in the sky to us, we measure, we can compute the angular distance. And if that object is at a redshift z, we can compare it with what our model would compute, given what these parameters are and given what the Hubble constant is. Well, we know the parameters pretty well, given the structure. What kind of objects could we use to compare DMZ computed with DMZ observed? So these are structures at maybe various redshifts. And what is done is the following. The so-called BOSS, or Baryon Oscillation Spectroscopic Survey, is part of the original Sloan Digital Sky Survey, the SDSS, which is giving us a three-dimensional picture of the distribution of galaxies. That's the actual facility there. It's Apache Point Observatory in New Mexico. And what it does each night, there's a template. If we look closely, it's can't see it on this scale, but that's an aluminum plate that is, holes have been drilled. Approximately 600 to 1,000 holes have been drilled at the positions of the focal plane of that telescope. It's about 100-inch telescope. Each one letting the image of a galaxy through. So you've got 600 to 1,000 holes there, each one allowing the image of a particular galaxy to go through. That gets light piped to a spectrometer, and it measures the spectrum of these galaxies. Now the spectrum is going to give you the redshift, so it'll tell you at what z, what redshift parameter these galaxies lie on. So this has been going on since 2000. For 20 years now, it's been taking data, and it's observed millions of galaxies. And this is a slice of the sky. This is the Earth at the middle. Then as you go out towards the perimeter, you're going back in time and out in distance. You can see that redshift parameter z on that horizontal scale there on the going from the position of the Earth to the right. it goes up to about 0.6 or 0.7 in the redshift parameter. That's billions of miles out, billions of light years out. So that's been an effort that has cataloged, again, billions of galaxies. So if you take galaxies, all the galaxies at a given Z, okay, take galaxies at a given Z and then search for structure. The structure that was imposed on the cosmic microwave background radiation at decoupling, of course, the structure in the microwave background radiation reflected structure in the baryons and dark matter distribution in the universe at that time. And that structure simply continues to grow as the universe expands. It expands with the universe and is reflected in the structure that we observe in the distribution of galaxies. So by taking different slices of this galaxy survey and examining the structure of these slices, you can determine by observing the angular angle in that the structure has one side to the other, you can compute from these observations an angular distance. So you get something like this. Here at a redshift of Z equals 0.57, which is quite a ways out into the universe, you take all the galaxies at that redshift and you look for structure and you see there's a bump at about 150 megaparsecs, which indicates this is how the structure, how that first peak in the cosmic microwave background radiation has been stretched by the expansion of the universe to the time when the redshift was 0.57. So that's the physical size of that dominant structure. We can measure the angle and we can compute the angular distance, divide by the physical diameter by the angle, observed angle of that structure from one side to the other. And you get that, dm, d sub m. Then you compute d sub m, assuming a value for the Hubble constant, and you change that value until you fit all of the observed d sub m's with the d sub m's you calculate at various redshifts with this model of the universe, this lambda cold dark matter, which seems to fit all the other things that you observe. In doing that, you get a value for the Hubble constant, which fits this data. This is, by the way, this is called baryon acoustic oscillations. It's the structure imprinted on the distribution of galaxies by the initial structure that was around when the matter decoupled from the radiation. Well, you do that, and here's what you end up with. The Hubble constant, as given by the baryon acoustic oscillations, is given, I quoted the Planck results, 2018, 67.7. A very firm value. I mean, there's very small error there, as you can see. And if you compare that with the way in which the Hubble constant was computed directly, you can see that that's the blue error bars. The blue shaded area is the value of the Hubble constant computed directly. The red is the value of the Hubble constant computed from the baryon acoustic oscillations and all the other structure that we talked about. And you can see they're converging, each is converging, but they're not converging to each other. There's a tantalizing difference there that's unresolved. So it's suggested that something's wrong somewhere, or something new has to be added and to what we know. And that's the situation today, and that's the end of my presentation.
Can I ask one more question?
Sure.
It's at the end, this discrepancy is actually most of these measurements based very strongly on the redshift itself, on most of this effect. Now, is it taken into consideration? Would the dark matter have any effect on the redshift itself? But we don't know.
I don't think so. I think
Can it be that cleansing effect, something, since they are kind of having a amount of matter, all those photons?
I'm not quite sure what you're asking, but the redshift, all that follows from extrapolating back from the present redshift to the time when decoupling took place and the temperature was 3,000 degrees. That's pretty straightforward physics that is not in dispute.
Yeah, that is possible. I can see that. But just generally, what effect could the dark matter have on those photons which are responsible to show the redshift?
The dark matter,
They could have the lensing effect.
they wouldn't have, I don't think they'd have an effect on the overall redshift. The redshift just comes about from the difference in the scale of the universe. The dark matter would affect the rate at which the universe was expanding at various times. It would affect h of z. It would also cause the dark matter. Presumably, is not distributed uniformly. It tends to be concentrated where galaxy clusters are observed, and that causes photon paths to be bent gravitationally.
Yeah.
You get what's called lensing, a
That's
lensing
what I mean.
effect, where distant galaxies that lay behind clusters of galaxies, as the photons propagate around these clusters of galaxies, the gravitational effect of the dark matter, along with the ordinary matter, bends these and distorts the shape of these background galaxies. So it does have an effect in that way, but it contributes, along with the dark energy and the ordinary matter and the radiation, if you go back far enough, to the critical density of the universe. It adds up to a critical energy density, which of course governs the expansion rate and the geometry of the universe. So it has effects here and there, but as far as just redshifting is concerned, I think it's all that's pretty straightforward. Any other questions?
Steve, you were great.
Well, thank you.
You were terrific. I understood 7% today.
Well, that's better than the usual 6.
I know.
I'm encouraged.
Me too.
That's very
See ya.
interesting.
Well, I see you stuck through the whole thing. I'm
I'm going to stop the recording now.
okay.